Hey guys, Adam with FANUC. Going to talk to you a little bit today about optimizing your robot's position within a work cell and the great tools found within RoboGuide that can help you do that. You will often be tasked with fitting a robot into tight spaces, or your mechanical engineers come up with a grand layout of conveyors and magazines and racks and assembly stations and fixtures, and now they have to put a robot in there. Now, how do you know how to get that robot perfect such that you have no reach issues, no singularity issues, no collision issues? Position it for the best possible cycle time for the motion and the kinematics of the robot. How do you know how to get that perfect the first time? All right, you don't. That's why we have RoboGuide. So I'm going to show you a little bit how this works. Obviously, we're going to start with a really dumbed down work cell here. Just a pick and a place location, equidistant from a small little LR mate. Just something to get the point across so I can show you the tools that you have. So here's a quick little program that I concocted. Set my frames, set my speeds. The robot will start at the home position, shown here. Then we go to a pick position with an approach and a retreat. We'll go to a place position with an approach and a retreat, and we'll go back home. So let's first, in order to understand how to position the robot best, first we have to understand the data and the metrics that are going to help us make that decision. So let's run this robot real quick. Run this program, pick, place, and home, okay? And let's learn a little bit about what RoboGuide can tell us. In our tree here, if we go down to profiles, you'll see it in your list down here, profiles. Here's the one that I just now ran. It's time-stamped. I ran the program called position test, which is true, position test. I'm going to right-click and look at my profiler data. Right off the bat, we're going to see the cycle time for this robot to run that path, 6.4 seconds. If I had some delay times for grippers or weight statements in the robot, we would be able to see a breakdown of what percentage of my total cycle time was spent sitting still versus spent in motion, and it breaks it down on an overview level. But we can get a lot more granular than that. We can look at the code that I wrote, home, pick, place, home, and we can look at the execution time for each individual motion and see how long it's taking to get to these places as sums of pieces of the sum total. Next, moving on, we can get this duty information out of RoboGuide. RoboGuide gives us a nice little key that says, hey, anything in green, you're great. If we start seeing things in yellow, you might want to do some testing. And if you get results in red, bad news. There's going to be an alarm. So RoboGuide can actually tell you, are you over payload? Are you trying to move too fast? Are you twisting the axes in bad manners? Obviously, for a dumb little pick and place, this robot is happy as ever. We're at room temperature, about 70 Fahrenheit, so we're in an air-conditioned climate. Let's go ahead and put this thing, on a tropical island somewhere. This robot is still happy, all right, even in the Arizona desert, right? This robot is happy. But you can see running cooler helps our heat values for our servos. So in this environment, you can see that axes 2 and 3 are pretty much doing all the work, which makes sense. It's doing just a lot of up and down, back and forth, so makes sense. We're also looking at our OVC, our voltage and current values. Obviously, this robot is not working very hard to get this job done. So this is good. This is the type of results you want to see, that the robot is performing well. We can also look at power info. If your kilowatt hour cost where you live is somewhere around 5 cents or so, it's going to tell us that, hey, if we work 20 hours a day, 300 days a year. That's what your electrical costs are per kilowatt hour. It's going to tell us how much power that robot's going to use in a year and what it's going to cost. So you're going to pay, your electric company $65 a year to run this robot. That's pretty good. We can also look at power motion analysis, looking at our power consumption, motor speeds, the torque exertion, what we're feeling in that profile over time. We can look at our reducer life, which is really important. How long will these gears hold out? Again, if we're running 20 hours a day, 6-second cycle time, 300 days a year, every single reducer on this robot is happy. We're looking at 100,000 hours mean time before failure. You can see J2 is about 3/4 of a million hours, right? Before, or 748,521 hours. So life is looking pretty good for this robot. We can also look at, individually look at each axis and look at the reducer speed and torque that it's feeling nice and low. Okay, so tons and tons of data. It's fun, right? Let's talk about how we can use that data to position the robot. I'm going to go to the back here. It'll be a little easier to see. Okay, tools, optimize position, utility menu. So right here under the RoboGuide tools, we can click this. We get a nice little pop-up screen. Okay, you just read on through. What robot? Well, I only have one. What program? Yep, position test. What do I want to do? What target do I want to play with? Do I want to move the objects in the work cell, or do I want to move the robot? Right now I want to test where this robot should be placed in the work cell, so I'm going to leave it here. And then in reference to what? I'm going to say in reference to the base of the robot. Here is my pitch. How far do I want to move this robot per iteration? Okay, so if I bring this down to say 50, and I say, all right, I want to test moving the robot. You can see every time I click, it goes in that pitch increment, 50, 100, 150. And while I'm doing that, you might notice that as I'm clicking, you're seeing this little blue line start to develop. Let's go forward. You're seeing a little blue line develop in the X direction of the robot. Let's do some in the Y. Negative Y, positive Y. It's starting to show you all these nodes, okay, where we're going to test the robot. All right, so right here's the, if I look top down, the 0, 0 where this robot currently is. RoboGuide is going to execute this program here, 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 here. It's going to take the robot and physically move the base of the robot to all these nodes on the grid. Let's give it some Z. Down, up. Everywhere you see an intersection, RoboGuide is going to put the base of the robot down at that intersection. So for example, it would put the base of the robot down in this corner, run the program, gather the profile data, and then let you know how it's doing. Okay? For the sake of this video and for the sake of all of our time, I'm going to do something a little more drastic. And I'm just going to say we'll just do a couple major iterations. There we go. So I changed my pitch to 200. So if you look at the top here, the robot's going to be tested 1, 2, 3, 4, 5, 6, 7, 8, 9 places on that top layer times 3 layers. This robot's going to run that cycle 27 times and give us a report. I'm going to click, yes, I want my duty info, I want my power info, I want my reducer info, and then all I have to do is click execute. Yes. So as you're watching here, you'll see the robot physically on the screen moves to these nodes, runs the program, moves to the next node, runs the program, and it's just going to run this loop. You can see how it's kind of really stretched out in that position, and some of these closer ones, it kind of starts getting a little tucked in. That one ran pretty good. That one's really tucked in on itself, but it made it. And what's going to happen is as it's gathering this, you know, no, what I like to do, if you got a lot of iterations with small pitches, hey, set it up, click execute, go take your lunch break. When you come back from lunch, RoboGuide is going to tell you where to put that robot in your final design. So let's let this thing keep humming along. We're about halfway done here. You'll see some of the clips zip through real quick. Those are, you'll see in a minute, but those are failures. That's where, hey, a robot at this position isn't going to run. And so it just hurries up and blips through and moves on with life because it knows that that's a bad place to be. So here we go. We're getting close to the end. Perfect. Okay. If you fast forward the video, welcome back. So at the end, the optimized position utility gives me this perfect little grid full of very useful data. Okay, let's break this down. The first thing you're going to notice is little red X's. Okay, this is where if you put the robot at that position, it will not run. Red X, bad. If I click preview and then click on one of these, you can see over on the screen, it puts the robot there. So if I was at -200, -200, -200, right, as far back over and down as I could get, then yes, the robot is not even going to be able to complete the task, likely because, yeah, it can't get to the blue area. So look at this data, all right? What can we do with this? I can sort this by, what order were they tested in? Let's sort it by cycle time. Now, it put all the bad ones at the bottom and it put all the good ones at the top, and it's telling me if I put the robot at that position on the table, I can get this work done 6.1 seconds if I max out the robot at 100% speed. And look at my overheat. Remember we were looking at those charts? Overheat value, 58 is actually a really good value. That's really low. Let me open this back up for reference. If we look at our duty information, 58%, that's super, super low. It'll turn yellow when you get above 80%. It'll turn red when you hit 100 or more percent. So overheat value is good. OVC is good. Power is good. This is the overall capacity of the robot, just kind of an overall scaler, so we're at like 15% of what this robot's even capable of. So we're really not even tasking this thing at all. But if you look around, we can click on this. It'll update and show me on the screen where that is and make those updates. Okay, so now you can start clicking through and you can look at each of your joints' overheat values, what those are looking like. You can see that at this position, J3 gets beat up a little bit, 71%, a little sketchy. We can look at our anticipated life. Again, these reducers are pretty happy, but if any alarms, if we set up our collisions, it'll let me know if I'm banging into things. If I click, in fact, I think if we scroll down here, we have one of these kind of a duds. This position, the robot can almost get the job done, but you'll see that it anticipates an error for limit, which is group 1, axis 2-3 interaction, which means this elbow kind of folds in on itself. So it's saying, hey, this would be a usable position if you could back it up just a little bit. So use this, and then here's the best part. When you figure out where you want the robot and you pick your favorite spot, all you have to do is come down and hit this button that says apply. And when you hit the apply button, it'll update all of your programming. It'll update your position. It'll update everything. And now your program is ready to go. I also want to point out that we have an export key. You can click export and it'll send all this data out to an Excel .csv file. But I'll pick that, say apply, and then the robot's there, updates the program. Let's do something a little different. Let's put it here and say apply. Apply. There we go. And so with that applied, now my robot is at my new position. Obviously, I didn't pick the best one. It's no surprise that For this setup, equidistant, putting the robot in the middle makes sense. But if you had a lot of stuff going on, working in front or behind, or if you had a really high speed application and every millisecond counted, please, tools, optimize position utility, set up your variables, execute it, get that information back, and now you can place a robot perfectly the first time, every time. All right, thanks for watching, guys. Any questions, put it in the comments or contact FANUC at 888 FANUC US. Have fun coding.